Hello and welcome back to ECMath. Today we're going to look at exponential equations, which may or may not require logarithms to solve. Not every equation is going to need a logarithm, but those that do really need it. So I am assuming you're sort of familiar with the properties of logarithms. Because they are exponential equations usually, it's also very helpful to review the exponent rules, and we maybe haven't used those in a while, so we're going to run through these in just a quick minute. First, if you have same base and you're multiplying those bases, you add the exponent. So this would be 3 to the x plus 2 as an exponent. If you're dividing the same bases, 3 to the 5x over 3 to the 2x, that is the same as subtracting the exponents. So that's 3 to the 5x minus 2x, which you could write as 3 to the 3x. If you have a power of a power, so 3 squared to the x plus 1, which maybe you'd see as 9 to the x plus 1, you multiply the exponent. So that's the same as 3 to the 2 times x plus 1, and you could distribute that out, 3 to the 2x plus 2. If you have negative exponents, that turns us into a fraction. 3 to the negative 4 is the same as 1 over 3 to the 4, or 181. And fractional exponents are the same as roots. So 81 to the 1/4 is the same as the 4th root of 81. And that's saying what number to the 4th power is 81, and since 3 to the 4th is 81, this simplifies to 3. One more property I didn't write here that's kind of a combination of these is if you have 81 to the 2/4, that's the same as 81 squared to the 1/4 power, the 4th root. But you can also think about it as the 4th root of 81 squared, and since the 4th root of 81 is 3, that's the same as 3 squared, which is 9. So if you have sort of nested fractional exponents, you can also use other properties. Here are all those rules in one. Make sure you're familiar with them. If you need any extra practice, please let me know. So the first type of exponential equation we'll see are those which you can solve by matching the base or already having a matching base. So let's look at equation A here. 4 to the 2x is equal to 4 to the 3x minus 10. Well, the base is the same. So what we're going to do is extract the exponents and just set 2x equal to 3x minus 10 and solve. So why don't we take away 2x from both sides and add 10 to both sides. So we get 10 equals x. And look at that. We are solved. Now here's an example of equations where the bases don't immediately match, but they both kind of smell like 3, don't they? So that's where we're going to try to use our exponent properties and express the bases as matching and then solve. So 1/3 is 3 to the negative 1, and then that's still raised to the power of x plus 12. And 9 is 3 squared, and that's still raised to the power of x. We just went over the power of a power property, so this is the same as 3 to the negative x minus 12, distributing that negative 1 to both terms, and that's equal to 3 to the 2x. So we can now extract the exponents and solve this equation separately to figure out what x would make those expressions equivalent. So let's add x to both sides, and we're not going to move the 12 even though it's negative, because we get negative 12 equals 3x, so negative 4 would be x dividing by 3. You don't always have to have a variable or even an exponent to solve using this idea. So we have 5 to the 3x minus 6 is equal to 125. Well, we could maybe solve this with logarithms, but it's going to be a lot easier to recognize that 125 is 5 to the 3rd. And here we have 5 to the 3x minus 6. So let's just extract those exponents and independently set them equal to each other. Add 6. So we have 3x is 9 and x is 3. You can check that this is true, of course, because you could maybe go 5 to the 3 times 3 minus 6. Oh, that's 5 to the third, which is 125. So that's a true statement. And you could have done that with all of these other ones, is always plug your answer back in if you feel like you need to check. So to summarize this general strategy, for exponential and logarithmic equations, we've been doing exponential, but you previously did this with logarithms as well. If you have a matching base equals, you can equate the exponents. You can conclude that n is equal to m. And the log property says the same thing. If you have a matching base and an equal sign, you can conclude that the insides must be equal. This property does have a name. It's called the one-to-one property of logs and exponential functions. And it is only a property that you can use on logs and exponential functions. It's not true in general. So as a sidebar over here, let's think about something like quantity x squared equal 2 squared. That's a very simple true equation, but it doesn't mean that x is 2, because if you solve this, x could be 2 or minus 2. And so we have like an extra solution because to actually solve it, we have to take a square root with a plus minus. Similarly, from trig, which you maybe remember from the past, sine x equals sine 45 does not just mean that x equals 45. That is one solution, but x could also equal 135, which would be the same sine value, right, as the y-coordinate, but in the second quadrant. Or x could equal 405, which would be 360 plus 45. There's other solutions other than 45. So in either case above, there's other solutions to be found. So why does this work for logs and exponents in general? Well, the name, this is very messy here, the name tells you sort of why it works. The one-to-one property is all about how logs and exponentials are both one-to-one functions. That is, they pass both the horizontal and vertical line tests. So every x maps with exactly one y, which means that even if we get rid of the function itself and we just look at the inputs, we're still going to have a match between the inputs, even if we get rid of the function. On the other hand, x squared looks like this, does not pass the horizontal line test, and neither does sine x. So those are not one-to-one functions, so you can't use something called the one-to-one property on them. Just as a sidebar, sometimes folks get excited about log equations and start trying to apply that property in situations where it's not valid. But for us, it is something you can do with logs and exponents anytime you have those. So, part 2. What if you have an exponential equation, but you can't get the bases to match? There's no way that you can get 4 to have a base of 15, other than maybe solving a separate logarithmic equation. So we're not going to do that. Instead, we have a number of excellent methods. The method that I prefer is to take a logarithm of both sides. We're going to take the logarithm of both sides. And because a logarithm is a one-to-one function, you can apply that function to both sides without changing the answer. So I'm going to take the log, and what I'm going to do is take the natural log, not because it's very convenient or the bases match, but because it's a very standard thing to do. It's just a habit that I am personally in, and I think that you should be in. Whenever we're solving, we don't need to think about what base log to take. You just take the natural log. So if you take the natural log of both sides, then this would be saying natural log of 4 to the x is equal to natural log of 15. Well, now that you have a logarithm on both sides, you've unlocked all the wonderful properties of logarithms, including the property where you can bring a power out to the front. So this could be the same as x natural log 4 equals natural log 15. I'm going to omit those parentheses. They're not needed now. And we want to find x. Well, this is times natural log 4, so let's just divide both sides by natural log 4. And we get x is equal to natural log 15 divided by natural log 4. It is okay to divide both sides by a log, right? This is just a number. I don't know what it is, but natural log 4 is 1.38. So if you can divide by 1.38, you can divide by natural log 4. You have to, you can't divide by natural log without the argument, but you can divide by that. You can divide by any kind of log you want. because it's just representing some kind of number. So here we have a solution for x. Now, I want to show you another way to do this. We said we're going to take the log of both sides, and the base doesn't matter. So some of you might be saying, well, could I take the log base 4 because I have a base 4 here? You absolutely can. So check this out. You could take the log base 4 of both sides and solve this way. Now, log base 4 of 4 to the x by the inverse property is just equal to x. And you could also say, if you don't believe the inverse property, which I think you should, but if you don't believe it, you could say, oh, well, that's equal to x times log base 4 of 4, which is equal to x times 1, which is also equal to x. Well, shoot, we solved for x. That was like way faster, Mr. Eck. Why did you say do natural log when I could have just taken log base 4? Well, let's check this out. We have this property called the change of base property. And the change of base property says that if you have a fraction of logs, right, and these are both log base e, so we have, I'm not going to write it, but you have log base e of 15 over log base e of 4. That's the same as log base 4 of 15. Oh. So they are the same answer. They are the same answer, and most of the time, either form would be acceptable. Natural log 15 over natural log 4, or x equals log base 4 of 15. There might be some times where a question asks you to put your answer in a specific form. It might say, express your answer in terms of natural log. Then you would need to do this. It might also say, express your answer in terms of a single logarithm. Then you would need to do that. So my suggestion is solve however you want, but be able to change the base to express the form in the way you need it to be. Personally, I like doing this cycle. And this is, what I would love for you to be able to do. Solve by taking natural log, but then at the very end, change that base. And I know it's a little bit longer, but it's really showing off all the different log skills you know in the manipulations you do. One benefit to taking natural log of both sides is you don't have to think about it. You can always say, I'm always going to take natural log, instead of being like, well, should I take base 4? What base should I do? How does that work? You just say, nope. Every day I'm taking natural log. I think that's really nice because it gives you a first step you can always do. So I've summarized that over here. You always want to take the log of both sides. Any base is technically okay. Natural log is the most common. But you can always use change of base to see if your answers are the same. Let's do another one. So we have 2 to the 2x minus 3 minus 1 equals 2. There's one more step you always need to do before you can take the log of both sides, and that's isolate. Log or exponent term. There's no log here, but there is an exponent term. Because if I try to take the natural log of both sides, well, I certainly can take natural log of 2, and I certainly can take this natural log. But that plus 1 is going to mess me up. There's no properties if you have a subtraction inside a log. So we got to get rid of that 1. And the good news is there's just a constant on the other side. So let's add 1 to both sides and rewrite. So we have 2 to the 2x minus 3 equals 3. Now, we could again try to match the base here, but we have a 2 on one side and a base of 3 on the other side. No way to get these bases to match. So let's just take that natural log of both sides. Natural log here, natural log here. Don't need those parentheses, but I'll put them in. Bring the exponent out. So we have 2x minus 3 is the entire exponent times natural log 2 equals natural log 3. Now, we want to isolate x, but we have to use real legitimate math. Natural log 2 is a number, which means we have to distribute that to all the terms. So this is really 2x natural log 2 minus 3 natural log 2 equals natural log 3. I'm just distributing that natural log 2 to both terms. Now, I'm going to pay attention to what I'm looking for. I'm looking for x. So I need to add this to both sides. And even though it's a logarithm, there's no special properties about how you add it. You just add it like it's a number. Having moved that over, we will rewrite. And we're still trying to solve for x. So we're going to solve this by dividing by 2 natural log 2. And we divide this whole thing here by 2 natural log 2. So let's rewrite. I'll try to stay on one screen. So let's rewrite it over here. So we'll get x equals natural log 3 plus 3 natural log 2 over 2 natural log 2. Now, if the problem has said solve for x, you can probably stop here because you solve for x. Very often the problem will say solve for x and simplify your answer. And this answer has some condensing that we could do here. So how could we condense this further? So I boxed it, but let's just say, what if the problem asked you to do a little more? Well, natural log 3 is pretty happy as it is, but 3 natural log 2 is the same as natural log 2 to the third, or 8. And 2 natural log 2 is the same as natural log 4, bringing all the exponents in. Now we could do natural log of 3 times 8, so that would be the same as natural log 24 divided by natural log 4. That's a pretty good result because we have just a fraction of logs, but this is also a change of base situation. So we could finally write our final answer as natural log base 4 of 24. So if it asked you to simplify to a single log, I would go there. If it said simplify, but didn't say single log, I would maybe go there. All of these are numerically equivalent. You can type all 3 of those in the calculator, you'll get the same thing. So it just kind of depends on what the question's asking. Personally, I like going all the way, getting things as simple as possible, because that way there's no ambiguity. We all can agree, like that's the simplest, most condensed answer. You could potentially, from this stage, also take a log with a different base, like log base 2 of both sides. That would change the work and how you simplify it, but you would get the same result if you simplified all the way to the end, which is another good reason to simplify all the way, is that people taking different bases might have different middle steps, but you'll always get the same thing in the end. Now I want to look at a type of equation that is similar to the last one, but has an additional complexity. And this is the kind of equation that I really think you should be able to solve. Please pay attention carefully to these steps because it's going to be really hard to figure it out if you're not being careful at seeing what the steps are. So we have 3 to the x minus 1 equals 7 to the 2 minus x. There's no way you're going to figure this out with guess and check. I'll just tell you right now, that's what a lot of people try. You have mismatched bases, you have too much going on in there, and I'll give you a hint, they don't meet at nice even values. So we need to do some serious solving. And the thing to do is take the natural log of both sides. This is one where it's really the best strategy to do natural log both sides. Minus 1. Instead of trying to get cute and maybe take a log base 3 or a log base 7, because you're never going to get all the logs to go away with this, so you might as well just take a natural log and have it be equally nasty on both sides. All right, we now have an exponent on both sides that we're going to bring out. We're going to distribute all of the natural logs to all the terms, because natural log 3 here is just a number, and natural log 7 is just a number, so we're going to bring it into every term. That's minus 1 ln 3. Okay, we've gotten rid of all the parentheses. We've basically expanded this, taken it apart. We're now going to rearrange it so that all the x's are on one side, because right now we're going to have a hard time solving for x if we have 2 separate x's. So let's keep this term on the left and add x natural log 7 to both sides. And let's add natural log 3 to both sides. So those will cancel out when you add. And if we rewrite, we should get x natural log 3 plus x natural log 7 equals 2 natural log 7 plus natural log 3. We're getting somewhere. We can't combine these x's because they have unlike coefficients, natural log 3 and natural log 7, even though they're both natural log, can't combine. But what you can do is factor out that x. So this can be x natural log 3 plus natural log 7. And then you can divide by this, natural log 3 plus natural log 7, on both sides. And on this side, it'll reduce out. So you get, as a final answer, x equals 2 natural log 7 plus natural log 3 over natural log 3 plus natural log 7. And there's a lot of 3's and 7's in here. One thing to note is, I made some choices about what side I put x on, what side I put the logs on. If you're working with a friend or a neighbor and they might have made different choices, they might get a different result here. So it's important to be able to simplify the result and see if you got the same thing as a friend. So again, if it said solve for x, technically you're done here. You've solved for x and you can stop. But if it said solve for x and simplify, then you need to keep going. And so we'll do that here. We're going to kind of condense this, though. 2 natural log 7 is 49, and then plus natural log 3. So that's the same as natural log of 3 times 49, whatever that is, 147, over natural log 21. And again, we could then use change of base to say that's the same as log base 21 of 147. And again, everybody that solves this problem will get the same result if you simplify it to a single log. And just to recap the steps, your first step is take the natural log of both sides, bring down all the exponents, distribute all the natural logs to all the exponents that you brought down, rearrange so all the x terms are on one side, and factor out that x. This is the step where folks usually get stuck, that rearrange and factor. But we've seen it before in other contexts. We're going to see it again in other contexts later. It's a really, really powerful trick that you should absolutely know. Then you're going to divide to solve for a single x. And if required, I recommend it, simplify the answer further until you get it down to a single log, using all your log properties. If you remember these steps, you can solve any equation like this. And it's actually usually not that bad. It might seem really intimidating at first, but by the time you practice it, you will be able to solve these. I really like this kind of equation because they let you do some powerful things. So why would you need to know this? Well, when you have two exponential expressions and they're equal to each other, what you're really doing is finding the intersection point of their graphs. So maybe you have an island where you have one population is growing, and another population is shrinking, and you want to find out where those populations are equal, or where will the system be in balance. You're solving an exponential equation. That's sort of in context. A problem you do all the time in calculus is say, hey, what's the area of this weird shape? How do you find it? Well, you find it by kind of cutting it into various little slices, but what do you need? You gotta know that intersection point. If you can't find that intersection point, you're dead in the water finding that area. So in able to find that area, which has all sorts of nice uses, you gotta be able to find those intersection points. And that's really why we solve log equations, is figuring out where two graphs meet. Where do two exponential growth or decay trends match up? Where are we in equilibrium? That's log equations. To finish us out today, we're going to talk about exponential equations in quadratic form. And as a fun brain break, I'd like you to take a second and multiply out u minus 1 times u minus 3. Did you work it out? Here it goes. So that turns into u squared minus u minus 3u plus 3, or u squared minus 4u plus 3. We'll just put that in the back of your mind for a second. And let's try another problem. What if I asked you to solve e to the 2x minus 4e to the x equals negative 3? Well, your first attempt might be, let's take the natural log of both sides. And if you're not being careful, you might say, well, can I just take the natural log of all three terms? And the answer is no. When you take the natural log of both sides, you got to take the natural log of the entire side. And at that point, you kind of get stuck because, again, we have no rules for that subtraction. There's nothing we could do here that would really get us moving forwards by taking a log. We got to break this up. So in the problem like this, we actually want to move all the coefficients to one side. We'll add 3. Get it looking like that. And then we're going to look for a hidden structure. When you see e to the 2x, think about our exponent rules. This is kind of like e to the x squared minus 4 e to the x plus 3. I haven't changed anything. But do you see that this and this are structured the same way, which means that they'll also factor the same way. So you can kind of say, hey, well, this is the same as u squared minus 4u plus 3, where u is equal to e to the x. This is called a u substitution. We've maybe used it before, but if you've never seen it, it's a really cool strategy. Just to use kind of a dummy variable to simplify things. Well, that would factor into u minus 1, u minus 3, based on the work we did above. So then this expression would factor into e to the x minus 1 times e to the x minus 3 equals 0. If you don't believe me, multiply those things back together with the e's in there and see what you get. You're going to get the same thing that you started with. Well, why would we bother with this? What is the point of this? Once you've factored it, you can use the zero product property. Remember, you have to have a 0 over here, but once you do, you can split this up into two cases. Case 1, e to the x minus 1 equals 0. And case 2, e to the x minus 3 equals 0. And solve each separately. So if e to the x minus 1 is 0, e to the x would have to equal 1. Hey, it's a logarithmic equation. We can take the natural log of both sides. So we get x equals natural log 1. Natural log 1 is 0. So x equals 0. Over here, we can again, we'll get e to the x equals 3. We can take the natural log of both sides. Natural log of e to the x is x, and x is equal to the natural log of 3, which doesn't simplify, so that's a second final answer. And this equation has two answers, 0 and natural log 3. And maybe, just maybe, you'd guess and check your way into solving this with x to getting x equals 0, but I very much doubt you'd get natural log 3 as one of the solutions unless you apply this method. So this is what I call a secret quadratic. When should you use this? Well, not every time. It's not super common, and when you need it, you really need it, but it's also kind of obvious that it's a secret quadratic because there's some like key identifiers. If you have 3 terms and one of them's a constant, so here we have 1, 2, 3 terms, one of them's just a 3, and you have a multiple of 2 in the exponent. You have that e to the 2x. These are the things you're seeing are going to have when you have a secret quadratic. And like stuff like that, it can come up with sine and cosine. It can come up in other situations, but it's always going to be this 3 terms, one thing squared, one thing not squared, that'll give you this ability to factor. And that's it. We've looked at a lot today. We've gone from the easiest of exponential equations to some really, really tricky ones. The next thing to do is get in there and practice those on your own. Let me know what questions you have, and I'll see you all next time.